Okay, so let us start our 25th lecture on power system operation and control. So today also we are going to see topic on security constraint optimal power flow. So everyone is able to see my screen, right? Okay, good. Let us see the video sometime later, but okay, this is going to be this way. Okay, so in this lecture, we have already seen the preventive and corrective control. I hope I have repeated this multiple times, so I hope this is clear to you now that how is it going to, what exactly is the difference between these two. We have also discussed this flow chart in length, and we have discussed these in detail, how the process will move on, how the cost will change. Everything we have discussed in detail in this slide. And also we saw about the base case OPF. I have already shown you a basic for the 2-bus example how this OPF will look like, the base case OPF will look like. We have already seen that. And also once we do this, after this base case OPF, once we find out that which all contingencies are critical contingencies and which all contingencies are the non-critical contingencies, based on these differences, we are now moving to the corrective rescheduling problem. So first we'll do the base case and then we'll go to the corrective rescheduling problem. And this corrective rescheduling problem is only done for the critical scenarios. So what all are the critical scenarios, we'll only perform this corrective rescheduling for those. And here in corrective rescheduling, we are trying to find the lookup table. Right, so the model looks like this, and here can anybody tell me what this last constraint is trying to do? We discussed this in the corrective rescheduling problem in the last class, what this last equation is trying to do here. Can anybody explain me? Am I audible to you guys? Okay, good. So what this last equation is trying to do here? Adam, Nivedita, Pratyasha, Arun, Devidas, perfect. So for a particular kth contingency, how much a particular generator can change, or in case of that, if that contingency takes place, what is the maximum margin available for a generator to change, and in a very small time span. So this condition ensures that how fast a generator can change in that small time interval and to satisfy the load. So let's say if a generator outage has taken place, so obviously some of the generator has to ramp up immediately to balance the generation and demand. Also, if let's say if a line outage has taken place, then again some generator has to adjust either to increase or to decrease based on the situation. It has to adjust so as to bring the system back to normal, or generation and demand balance should be ensured. So I hope it is clear to everyone. Come again, sorry, what do you mean? No, not exactly slack variables. It is actually all the variables. For example, like slack, yes, in the power flow you have seen one slack bus generator is there, which is kept free, and it can balance and adjust for the remaining losses and the generations. But here in the corrective rescheduling, we do not do this for the losses, and for that slack bus, it is actually happening with all the generators. So all the generators ramp up and ramp down limits will be ensured here, so that how fast a generator can ramp up or ramp down considering a contingency or a kth contingency has taken place. So when this kth contingency takes place, what is the optimal scheduling what the system operator has to reschedule so that all the generators can balance the load? So it's not exactly slack bus, it is all the generators actually satisfy that. So this is nowhere connected with slack bus logic, right? Yeah, we have actually, you can see the previous video, I have discussed this in detail there, and means you can just read that, we see that video and you will be able to understand the logic. Okay, good. Then we discussed that, yeah, okay, so I think we stopped here and we did not discuss this. Now from here, obviously most of the critical contingencies will be able to handle here, but assume that there will be some critical contingency, and we have discussed again this in the previous lecture, that let's say there is a critical contingency which is not solvable in the current corrective rescheduling stage. So what we do is basically we take that critical contingency and add that contingency in the preventive step, right? So we'll go to the preventive rescheduling and we'll add that contingency there. So let us see, when I say we have to add a preventive critical contingency at the preventive stage, what do I mean by that? So basically before adding that contingency, let's say when I talk about, you must have observed that whenever I say that in the operating states of a power system, there are one is a secure state, one is a correctively secure state, right? So actually nobody asked me that question during when I was teaching that topic, but can you tell me now that how can we ensure that the system is in secure state? I also mentioned that often the system is going to be at a correctively secure state, but how we can say that the system will remain in a secure state, or what we have to do to ensure that the system remains in secure state? Can anybody answer this? What do we have to do to ensure that system remains in the secure state? No, means yeah, but that is the case of all these states, that voltage angle and the voltage limits and the angle limits should be remain within the limits. So this is for all these states. Even at the correctable secure state, we have to ensure that. Even at the correctable emergency state, we have to ensure that. Even at the alert state, we have to ensure that. So basically at every state we have to ensure this voltage and those things. But how can you say that all your system system is operating in a secure state? What do we have to do here? Yes, exactly. So whenever we say that even if any contingency takes place, you must be not exactly backup. Backup is kind of an incorrect word here, because whenever we talk about backup, that means it is basically we are talking about the correctively secure state. So basically, let's say if a system is running at this moment and a generator is generating 100 megawatt, there is another generator which is generating 50 megawatt, there is another generator which is generating 20 megawatt. Obviously there will be many generators which will be generating at different values. All the loads are having their own consumption value. With this view of the system, any contingency if takes place, any contingency, either a generator is out or a load is out or a line is out, anything which is, any contingency which takes place in the system, the idea is that you should not be required to change the generation schedule beyond its ramp limit. So for example, let's say if a line outage takes place, that means you do not have to change the generation at all. Means basically you do not have to touch any generation. Every generator will keep on running in such a way that even if any one line gets out, then even then the system always remain at the secure state, or even then the generation remains at its original value. You do not have to change the generation setting. Now similarly, if let's say a generator gets out, then you have to only adjust that power balance by adding a small generation, which is by changing the generation set points based on the ramp limit of individual generator. So whenever a line outage takes place, you do not have to change any setting in the system. If a generator outage takes place, you just have to change some of the generator to ensure the balance, and with this, if you are able to satisfy the system, then you call that the system is in a secure state, right? Or in a simple sense, when yes please. Yes, exactly, you can say that. So whenever you say that because in preventive rescheduling we were skipping in the first step and we were only including the contingencies based on its critical and non-critical basis, or rather to be specific, only the critical contingencies which do not pass the corrective rescheduling step, we only include those contingency in the preventive step, and that's why we call it as preventive rescheduling. Now what Adam has said, he has said correctly that if we include all the contingencies, whether it is critical or non-critical, whether it is passing on corrective or not passing, just include all the contingencies at the base case itself. And once you do that, you by default arrive at a state which is a secure state, right? So perfect, Adam, and Nivedita also, you also gave the correct answer. Okay, so the idea here is you can imagine, I'll mention here that u naught, the objective function will be u naught x naught. That means the objective function is solved or is kept to minimize the cost on the base case, but all the constraints includes all the contingencies possible, all the cases what you can assume, all the cases will be here, and these cases will also be affecting these equality and inequality constraints. So basically you can see that for all k, you can see here for all k, let's say we were talking about our 2-bus system. Sorry, I did not brought the pen today. So this was the 2-bus system. Here basically how many contingencies can be there? 4 contingencies, 2 generators and 2 lines, right? So basically NC will be 4, and here you see K, we are starting from 0. So that means in the base case, along with all the 4 possible contingencies, in all the situation, your cost should be of the objective function should be minimum in the base case. So this is u naught x naught, so this is the base case, but your equality inequality constraints will include all the possible contingencies, and based on that you will write multiple equality equations, multiple inequality equations. For all these situations you have to write, and you have to connect all the variables using the ramp limits. So you can imagine the size of the system just for this 2-bus system is going to be 4 times the base case value. So because there are 4 contingencies, so it will increase 4 times. and you can see if we are talking about the practical system, the size is going to be the enormous size will be there, and therefore these type of cases are neither economically or computationally viable. You cannot solve this problem in a practical setup, and considering the size of the Indian grid, it is not solvable. So basically we never include all the contingencies at the first step. So that's what is the answer what probably somebody has asked. I think Arun or someone has asked during when I was explaining the flow chart, that why are we skipping the preventive rescheduling at the first step. The idea here is that if you include all the contingencies, it affects the economics. Obviously the cost will increase from the base case solution, and also it will increase the computational burden. So obviously in practical situation you need the results at just the snap of the at very fast time interval. You need the solution. So obviously if you are losing obviously on the economics, but also you are losing on the computational burden. So that's why we always ignore including all the all the critical or non-critical contingencies in the base case, and obviously it will increase the economics and the computational burden. So I hope you got the idea. The size of the problem will be huge. Now the question is how to include those preventive contingencies. So what we do here, let me just show you the next slide. We actually run the limited preventive rescheduling problem, and we actually include only the contingencies which are unsolvable in the corrective rescheduling state, right? So only the problems, the critical ones which are not solved or which are not resolved in the corrective rescheduling stage, only those contingencies we take to the preventive rescheduling, and that's what we have seen in the flow chart when I was explaining that. So only those contingencies you will take here, and then you will add this ramp constraint to ensure that the generators are ramping up properly. So only you will take, so you can see here that here every time K is here, because K for all the contingencies, and K is starting from 0, so you can assume it is for the base case also. And here you have objective function which is only for the base case, right? Now it's clear, right? It's clear to everyone what is limited preventive rescheduling. So we will limit only to the unsolvable cases in the critical in the corrective rescheduling stage. Now here one can see that the size will reduce drastically, because obviously there will be very limited critical contingencies which are not solvable at the corrective state. So you will basically land up with very less number of increase in very small increase in the problem size, and this problem becomes very easily solvable using any personal computer problem, and it also does not increase the economics much. Obviously you are reducing the economics as well as the computational burden. Now here I also told you previously that once you run this limited preventive rescheduling problem, you again have to run a security analysis. And why do we want to run again the security analysis? Can anybody answer this? Why do we again need to run the security analysis for preventive rescheduling? Anyone? Why do we want? No. I'm talking about security analysis, because after we go for preventive rescheduling, we have to go to the security analysis again after the preventive rescheduling. Why do we want to go to the security analysis again? That's what is my question. Probably Adam, Arun, Devidas. Exactly. Please answer. Yes, because we are not at the same base case. So because we are adding a contingency here in the base case, not is always a base case. The circle is always the base case. So as soon as we are changing the base case, you are changing the critical and non-critical contingencies also. So basically you have to again run the security analysis to know that if the same critical contingencies are still critical, or there are new critical contingencies, or there might be a contingency which was earlier non-critical, and because of adding this contingency here, this has become a critical one. So anything can happen. So basically you have to rerun the security analysis to identify the critical and non-critical contingencies. Based on these critical contingencies, you will again feed that critical contingencies into the corrective state, and then you will try to find the lookup table, and if you are able to solve all the critical contingencies, then it is fine. You will go to the next time interval. But if let's say you are unable to solve it, and the problem still persists, then you will again go back to the preventive rescheduling, and you will add another contingency here, and then again you will get the new base case solution, and then again you have to form the security analysis. So this iteration keeps on running until and unless we resolve all the critical contingencies, right? So this is the way we do it. So is there any query as of now? I hope the flow chart is clear, the mathematical expression is clear. Is there anything which is not clear as of now? Okay, good. Anyways, I'm happy that no queries are there. Let us just go ahead. But what here issue is that even after all these simplification, the preventive rescheduling problem is still a difficult problem to solve. I actually did not brought pen, but I can write just for that 2-bus problem, and I can show you that the problem is still becomes complex for even for 2-bus system. Although yeah, it is very easy to solve from the computer's point of view, but still it increases the number of variables and number of equations, and you have to incorporate a lot of things into that. So basically, to even further simplify the preventive rescheduling problem, there are 2 steps. So the one step is the limited preventive rescheduling problem, which we have already discussed. That was basically you identify the infeasible cases at the corrective rescheduling state, and then you pass on that infeasible cases in the preventive OPF, and you append those contingencies into that. So that we have already seen. Now the second problem is basically something innovative and something creative was proposed recently, where they said that okay, even if we have some contingencies, we can even further simplify the problem. So let us see how they have proposed that and how they can simplify the problem. So basically the approach one was we just discussed, that is the limited preventive OPF problem, preventive rescheduling problem, where you will only include the contingencies which are infeasible in the corrective rescheduling state. So this we have already seen. So this is clear to everyone. Now in the second approach, what we can do is basically we can see that what all contingencies are becoming infeasible in the base case, at what value. So for example, let me just show you the model, and it will become very easy for everyone to understand, and you will be happy to appreciate this problem. Basically, let us talk about any kth infeasible contingency. kth infeasible means there is a critical contingency which is not solvable by the corrective rescheduling step, right? So for that kth infeasible contingency, what you have to do is basically you have to form this equality equation. This is fine, this you can do. HK, this is the inequality equation, which is again you can do. ET is actually the unit vector, so you are just summing up all the ZKs, and ZK is a continuous variable where ZK is greater than equal to 0. I forgot to mention that this is ZK is greater than equal to 0, and then you mention here delta UK max plus ZK and UK minus U naught, and U naught is the solution from the base case. Now what is happening here? Basically, I can easily explain you this from a practical example, and then I'll explain you this mathematical model. Think from the point of a transmission line, that generally transmission lines, let's assume a line is there which is having a manufacturer rating limit of, let's say, 100 megawatt. 100 megawatt is given by the manufacturer, and if 100 megawatt is given to by the manufacturer, that means basically if power flows beyond 100 megawatt, then this wire will burn or it will get damaged, right? So basically system operator cannot afford to allow power to flow on this line beyond 100 megawatts. So that's what is ensured by the system operator. So let's say this line is there which is generating which has a manufacturer rating of 100 megawatt. Now you know from the basic understanding, even if you can see all the regulators document, you will see that system operator generally operates at 80% of the maximum limit or this limit. So generally system operator, instead of 100 megawatt, obviously practically the actual limit is 100 megawatt, but to ensure safety, system operator ensures only 80% of maximum capacity. This is valid for all the generators, this is valid for all the lines, because they do not want the machine or the lines to hit its maximum limit and may create damage, and if a damage is happening, that means that is irreparable, because you need to again reinstall the new line and it takes a lot of time. So generally nobody does that thing, so they always operate all the machines in the power system at roughly around 80%. Every regulator has its own limits, but in India we operate at 80%. Right, now let us come back to this equation. Now you got this idea that the lines are operating at 80%, and what does this mean is that this line will be limited by 80 megawatt and not by 100 megawatt. So what will happen is, in this equation, if you see the last equation, here we are adding a ZK variable which is a continuous variable, and you are adding this in the objective function, and you know that the base case solution is U naught. Right, so let's say on this line from the base case, you saw that the flow on this line was, let's say I'm just giving an example, that this line flow was 70 megawatt in the base case, right? Then there is some kth critical contingency, it can be anywhere. Because of this critical contingency, the line limit is moving to 90 megawatt. Let's assume that. So with the kth contingency, the line limit is moving to 90 megawatt. So obviously as soon as the line moves to the 19 megawatts, it is not solvable in the critical contingency state, or sorry, corrective state. So this contingency will be added to the preventive step. Now with this optimization problem which we are seeing here, in this optimization problem, what are we doing is basically we are seeing how much we can relax the maximum limit, by how much value we can relax this maximum limit, so that this critical contingency can be solvable, right? So The second approach, name suggests, it is a restoring feasibility of the infeasible post contingency. So just by the name also, we are just restoring the feasibility by seeing that how much maximum margin we can push so that still our problem of this infeasible contingency is solvable. So you can see here, earlier it was 70, it was fine, everything was fine, but because of this kth infeasible contingency, we see that it is going to increase the power flow by 20 megawatt eventually to 90 megawatt. So what you will see that here for this kth contingency, Zk will come out to be 10, because by increasing 10 megawatt capacity of the line, you can solve the problem. Now this is a decision of a system operator. So system operator can see that, okay, I generally operate at 80% of a main capacity. Let us increase it by just by 10% and ensure that the problem, this critical contingency, is already taken care of. Now the problem, now you can imagine why he can relax this, because actually the contingency has not taken place. We are only planning, this is all happening in the planning stage, that in operation when the system is running at a base case, any random base case, and we want to see that, okay, if a contingency takes place, then what operational changes we have to make to satisfy the system. So that's what they are planning in the day ahead, and planning it that, okay, if contingency takes place, what we have to do. So that's what is called as this step is called as restoring feasibility. And then you will run this and you will get the optimal values of UK and ZK, and then what you can do here, this problem becomes even more simpler, is basically we'll fix the values of ZK and UK, we'll fix it whatever the optimization problem is given for this kth contingency. And in the modified preventive OPF, in the approach 2, what you will do, you will just run the base case. So here you just have to run the base case, and for the rest all kth contingencies, you will just add the UK star which you got from the previous problem, and the ZK star from the previous problem, where you are just assuming that if that particular contingency takes place, how much you have to change the base case. And here you will, based on this constraint, and this constraint will be there for all K contingencies, what all critical contingencies which are coming from the corrective rescheduling step, you will add all those K contingency here, and there will be, or these equations you can see, this will be only just once because it is only for the not or the base case. This equation will be like multiple equations will be there, and this will correspond to all the critical contingencies which are not solved in the corrective step. So you can see here the problem size is again back to the same base case problem, only this inequality is additionally added. So you can see how drastically the problem size has reduced. So this is the complete mathematical model and the way we add the critical and non-critical contingencies in every preventive and corrective step. Right. So is there any other query, or everything is clear, I hope? This looks simple, but it is not. You have to just visualize it. So let me just, if there is any query, I'll just pause for a while so that. Okay, good. So we will do the example in the tutorial, and then things will be even clear. Okay. So I have not prepared any example for this now, but it will be done in the tutorial and things will be much comfortable there. Okay, so